So in this problem or exercise, we want to show that the point of discontinuity of a monotone function is in fact countable. So for that, we will follow, of course, the previous problem that we did, which shows that either the limit does not exist. We know, first of all, that if f is monotone increasing, keep in mind that we can always assume that f is monotone increasing because we have seen in the previous example that f is increasing if and only if minus f is decreasing. So we just need to prove for one and then we have the other one. Okay? If f is monotone increasing, then okay, for any x0, inside the domain, then we have the existence of limit from the left less or equal than the value of f at x0, less or equal than limit from the right. So in other words, the limit from the left and the limit from the right do exist, and they squeeze f of x0 in between. Okay, so if the function is continuous, then the two limits exist and it's equal to f of x0. Okay, but if it's not continuous, then we have the limit from the left is strictly less. So here, what this tells me that x0 belongs to D. Okay, uh, and let's say between A and B, inside A and B, to make sure that we are interior. Okay, otherwise there is no problem. We can still talk about the right limit at A or the left limit at B. So if we take this, then in this case what we have because f is discontinuous, we must have limit of f of x when x goes to x0 minus less, if and only if, in fact, okay, limit of f of x from the right. So when you have discontinuity, if and only if these two limits are different, okay, and one is strictly less than the other one. So what we're going to do is to show that, in order for us to show that D is countable, let's fix epsilon positive and consider D epsilon is equal to x0, which belongs to AB, such that the limit from the right minus limit from the left, this is less than, uh, uh, sorry, not less, greater or equal than epsilon. Okay? So we know in this case that they are different. Okay? And since epsilon is positive, this is different. And therefore, this d epsilon is going to be included in D. Okay? And what happened is that it's easy to see from what we did before that this is the union of d1 over n for n greater or equal than 1. So what's interesting is that what we are going to prove is the fact that d epsilon is in fact finite. So if we prove this, then this d1 over n will be finite, and then you have a countable union of finite sets. It will be what? Countable. So this is how we're going to approach it. Okay? So let us prove now that d epsilon is finite. So let x1, x2, xn belongs to d epsilon with, we can always assume this, less than x2 less than xn. Okay? It's very easy to show that for I equals to 1, 2, or n, we have, in fact, n minus 1, we have lim of f of x. It's a little bit complicated. Xi minus. So this will be less than lim of f of x when x goes to xi plus less or equal lim of f of x when x goes to xi plus 1 minus to the left less or equal than lim to the right of xi plus 1 plus. In fact, the most important one is this one here. Okay? Okay? So, once we have this, then what do we have? We can prove that f of a, okay, is smaller than all of them. And they are all smaller than f of b. F of b is the biggest one, and the of a is the smallest one because f is monotone increasing. Okay? So from here, we get what? That f of b, okay, that the sum, okay, because they are all increasing intervals. So the sum between limit of when x goes to xi plus minus limit of f of x when x goes to xi minus, this will be less than f of b minus f of a. And this is from 1 to n. Since every one of them, every piece of these ones is greater than epsilon, then you are going to have that n times epsilon is less than f of b minus f of a, which tells me that n is less or equal than f of b minus f of a over epsilon. So you see the number of points n in the d epsilon cannot exceed this number here. And therefore, this will imply that d epsilon is finite. Okay, one application of this, so now we know that d is countable. So what happens if our function is defined on the whole real line? Okay, remark. So what happens if f now is defined from R to R and is monotone? So can we still claim that the set D now, which is the set of x in R, such that f is discontinuous at x, is countable? Okay? So instead of having an interval AB, now we have what? The entire real line. The result will not change anything because your R can be is just a union, countable union of intervals. For example, R, we can see that is the union of minus n, n, n greater or equal than 1. So in this case, you just restrict your f to every interval. Okay, so you call them dn's. So dn is the set of x in minus n and such that your f of x is discontinuous at x0. So in this case, we know from the previous proof that dn is countable. And our d is going to be just the union of dn's. And therefore, we have what? A countable union of countable sets. Therefore, d is countable. So it doesn't matter whether you have an interval ab or a function that's defined on the entire real line.